Good morning. My name is Marek Drużdżel and I'm one of the partners in BayesFusion LLC, which is one of the youngest members of the EMDS consortium. I'm going to tell you briefly about BayesFusion, then spend most of my time on Bayesian networks and their relatives, show you one slide of architecture of Genie and Smile, and after the presentation I'll give you a brief demo of Genie. BayesFusion LLC started as a research lab at the University of Pittsburgh, where I'm also a professor. We developed Genie and Smile over a period of 20 years, have had several users, and became quite well known for the quality and functionality of the software. In 2015, we formed a company with some of our people, acquired license for Genie and Smile, and it's a commercial company, but we are continuing the tradition of the Decision Systems Lab in making the software available free of charge to academic use. Bayesian networks are acyclic directed graphs consisting of the structure of the graph, the qualitative part, typically mimicking the causal structure among variables, and the quantitative part, which are the numbers composing the joint probability distribution over the variables. The numbers reside in the nodes of the network. In those nodes that have no predecessors, we have prior probability distributions. In all nodes that have predecessors, we have conditional probability distributions, conditional on the predecessors. Bayesian networks are used to calculate the impact of observations on other variables. For example, if we want to know the probability of an invasive cervical cancer in a patient with high-grade dysplasia with a history of HPV infections, the cancer state is in the cervix node, observations are in the HPV and Pap test node. We can imagine that as spreading the information over the network and calculating the conditional probability distribution of interest, answering effectively the question that we are asking. Here is a network demonstrating the power of representation using Bayesian networks. There are over 2100 variables in this model. Brute force representation would require 2 to the power of 2100 parameters. This network is represented by just 12,000 parameters. Let me magnify the middle part of the node of the network. You see that this is a spaghetti of connections, and then the parameters 2 to the power of 2100 is roughly 10 to the power of 600, which is orders and orders of magnitude more than the currently believed number of atoms in the observable universe. Bayesian networks are very close to equation-based systems, systems of simultaneous equations in which some of the equations describe the interactions among variables and other equations describe settings for exogenous variables. A system of equations like this can be shown by means of a directed acyclic graph. That is work dating back to 1950s. Spreadsheet-based models are also an instance of a relative of Bayesian networks. You can imagine putting arrows between cells that feed each other. Of course, this kind of representation would not be very convenient because that would remind us of a spaghetti of things as well. Directed graphs of Bayesian networks are much better. Our software focuses on a representation that is a hybrid of systems of simultaneous equations and Bayesian networks. Here's an example of a hybrid network in which quite a number of nodes have equations and continuous distributions in them, and then you can also have discrete nodes and influences that are typical of discrete Bayesian networks. These are hybrid Bayesian networks. Our software allows you also to represent dynamic models, dynamic systems. Here is a somewhat naive, we believe, representation of dynamic models in which we have the same variables replicated in time t and t plus 1 and showing influences that span over time. The representation used in Gini is closer to graphical representations of systems of difference or differential equations. Every node is represented just once, and we show temporal arcs with labels of the temporal influence. We allow temporal influences spanning over several orders of time, which is a big step towards systems of differential equations with derivatives of various orders. The architecture of Gini and SMILE is quite simple. There is the API, Application Programmer's Interface. C and C++ are native to SMILE. And then we have several wrappers allowing the users to access SMILE functionality from Java, that's JSmile, from .NET programs like Visual Basic, and even on Pocket PCs like Android or Apple devices. And we also have a wrapper for direct access from Python. Gini is just a simple GUI, graphical user interface, working under Windows but also under Linux and Apple Macintosh. I will give you a brief demo after this presentation. The recent developments after we created the company are hybrid Bayesian networks, some of the ideas I showed you in this presentation. We also have an interactive model repository that can be installed at the client's user's site and allows local users on a local network to access the models and play with them. We also have smartphone apps for iPhone and soon for Android devices that allow to use this technology. Very soon, an exciting development for this community is support for map-based applications, spatial Bayesian networks, allowing us to perform calculation on individual grids of a larger map. We're also planning several enhancements to learning, such as learning dynamic Bayesian networks from time series and various algorithms and concluding remarks. Bayesian probability theory works. There are plenty of successful applications that solve real problems. Some people call 21st century the century of data. Others call it the century of Bayes. Gini and SMILE are popular in academia because they are free, but they are also a prime choice for commercial applications, and we have quite a number of commercial users. And it is our users who drive our development in terms of improvements and new features. So we encourage you very strongly to get in touch with us if you need help or if you have any suggestions for the future. Thank you very much. I'm going to give you a 5-minute introduction to Bayesian networks. What they are, how to build them, how to learn them from data, and finally, how to use them in practical applications. We will build a simple network that models an investment decision. We'll create two variables, chance nodes. The first one will be named success of a venture. Let's define that variable. We'll give it an identifier success and name success of a venture. This variable models the probability of a business succeeding. Suppose that the probability of a business succeeding is around 20%, which means pretty much that 20% of all small businesses, startups, succeed, and 80% of them fail. That's a prior probability of success of a new business. If we want to estimate the probability of success, we may ask an expert to give us an evaluation of this business. Let's call this variable expert forecast, or in brief, forecast. The variable is going to be defined as the forecast may be good, fair, or poor. I'm going to add another state of this variable to denote poor. Let there be a connection between the two. Typically, we interpret connections as causal connections. This arc, this arrow, means that success of a venture has a causal impact on expert forecast. In other words, the expert is guided by the potential success of this venture in her forecasts. If the business is going to be successful, let the expert give 40% chance of succeeding, the same 40% of a statement that the business is fair, and poor 20%. In other words, for all successful businesses, the expert will estimate them as good with 40% chance, fair with 40% chance, and poor with 20% chance. If this business is going to be a failure, the expert can still make a mistake and call it a good business with 10% chance, fair business with 30% chance, and a poor business with 60% chance. A Bayesian network is a specification of a joint probability distribution over a collection of variables. Once we have this collection of variables, we can perform inference with them. We can reason. The main type of reasoning in Bayesian networks is calculating the impact of observation on other variables in the network. To show you that, let me view these two variables as bar charts. At this point, we can see the states of each of the variables and also their probabilities. Success of a venture has 20% probability, failure 80%. Expert forecast, that's so-called the marginal distribution. Our expert calls 16% of all businesses that she's asked to evaluate good, 52% of them poor. And now, reasoning in Bayesian networks. I'm double-clicking on the outcome good, given that the expert said that this business is good, the probability of success of this business goes up to 50%. If the expert says poor, again I'm double-clicking on the state poor, the probability of success of this venture is only 8%. As you see, I can use Bayesian networks to calculate the impact of observations on other variables. This is their fundamental way of working. Suppose we have a data set. This data set has been collected at a bank. We are dealing with 10,000 records of bank customers who are measured on quite a number of variables, starting from payment history, work history, and ending at a variable called creditworthiness. Has this customer paid his or her loan back? We can learn a new Bayesian network from these data. I'm picking one of the algorithms which proposes a structure for this network. We are learning this structure. Let me reorganize it slightly. I'm going to view it as a bar chart. I'm going to expand the nodes a little so that we can see what they mean, and then also change the layout of the graph. Here we are. We have a new Bayesian network created from the data set, a Bayesian network that is immediately useful in predicting the creditworthiness of an individual applying for a loan. If this individual comes from a similar population to the population that we measured over time, then we can predict whether this individual will pay back the loan. Typical questions on a loan application: payment history, work history, income. I'm observing these variables, age, and as you see, all of these inputs, the data, are impacting the creditworthiness of the individual. So a Bayesian network that we just constructed can be used immediately in the same way that we used our small two-node network for predicting the success of a venture. We can predict whether this customer will pay a loan. Finally, a very large network consisting of over 2,000 variables, 2,127 variables, used for diagnosis of diesel locomotives. This network illustrates one more application of Bayesian networks. Let me first show you this model. It's an impressive model. I'm going to fit it to the window. Please note that it is really very complex. It models various ways a diesel locomotive can break and various symptoms of different failures of the locomotive. As you see, the network is very complex. Let me demonstrate diagnostic application of these methodologies. I have opened a special diagnostic window in which in the upper left corner we have all possible ways that the locomotive can fail. There are quite a number of them. And on the right-hand side, top right-hand side, we see various symptoms rank ordered from the most to least informative. Suppose we want to know more about this possible failure, which is the most likely one at the moment. These are the two most important tests. Suppose we are suspecting 4 of these different failures. Here are the tests that are going to be distinguishing among them most. If I choose something that is judged by the program not informative, then not much is changing among the 4. If I pick one of the top symptoms, test results that are judged to be very informative, you will see that a lot is changing among the possible failures. This demonstrated a diagnostic application of Bayesian networks, which have been very successful in diagnosis. This concludes my brief presentation. Please do not hesitate to get in touch with us if you have any further questions or if we can be of any help to you. Thank you very much.